that the force on the belt and the velocity of the belt and the diameter of the roller and then we should design the high-speed shaft. So we should determine the shape of the shaft and the diameter and length for each shaft segment. And then you should draw the parting the shaft, draw a shaft. Okay, shaft parting for this shaft drawing, and this is our course design. Okay, and first we should choose the type of the model. Okay, we should choose the type of the model, and do you remember how to choose the type of the model? Do you remember?
Based on the power required, we use the power required to choose PR.
Yes, we should load the required power for the mortal first. Okay, and then after choose the model type, and then we should distribution the speed ratio, and then selection and calculation the kinematic and dynamic parameters, and this is the table for the model type. And first, selection and calculation of model, we usually choose Y series type, okay? And then the power of working part. The working part is a belt, okay? Working part is a belt. And we load the force and the velocity, okay? And then the power of working part, the power of the belt can be calculated by this. This is the force on the belt, and this is the force, this is the velocity of the belt. And then we calculate the power of working part is 3.36. And then we calculation the mortal power. So how to calculate the required power of mortal?
We use the formula. PR.
We
We use
use
the formula.
yes, use the
PR
formula PR. Yes,
equals
and
EW.
it's PW times the total efficiency. Okay, total efficiency. So in there, we know that from mortal to the belt, there are two pair of gears. Okay, two pair of gears. And how many bearings? How many bearings?
Three pair.
One, two, three, four.
Four.
Four pairs of bearings. Four. One, two, three, four. Four pairs of bearings. Okay. This is one, two, three, and four. Okay. And one coupling and one roller. Okay.
Yeah.
Okay. So the total efficiency can be calculated by the scale of the efficiency of gears and horsepower, the efficiency of bearing. Oh, there are two coupling. One, two couplings. Okay, there is one, there is two, and consider two couplings and one roller. Okay, and then we should determine the efficiency of each component. Okay, there are 4 pairs of bearings, 2 pairs of couplings, 1 roller, 2 pairs of gears. And from them, we choose first, we choose the efficiency of gear. Usually, we choose 8 grade, and the efficiency is 0.97, and then choose the efficiency of bearings, and it's 0.98. Usually we choose roller bearing, and choose the efficiency of coupling is 0.99, and choose the efficiency of roller is 0.96. Okay. Oh, we lose the efficiency of gear. We choose accuracy grade is 8, and those the efficiency of bearing and efficiency of coupling, efficiency of roller, and then we can calculate the total transmission efficiency. Okay, the total transmission efficiency is 0.8166, and the power required for the motor is the required power of working part divided by the total efficiency. Okay, so the power required of the motor is 4.1146, and then according to the required power PR, we choose the motor type. How to choose the motor type? The rated power should larger than the PR. Okay, and in the table 90 to 1, we can choose. We choose the motor type under the synchronous speed as 1,000 or 1,500. Okay, so for this condition, the synchronous speed is 1,000. We choose which type? According to the rated power, the rated power should larger than the PR. PR is 4.1146. So tell me, you choose which type? Choose which type? Choose which type?
5.5.
5.6.
5.5.
5.5.
Yeah, this
5
one.
to 5.5. Okay.
Yeah.
Choose this type. Okay. Great. And then for the synchronous speed, it's 1,500. We choose which type?
Use
This one is
S4
also
5.5.
5.5. 1,
Yes.
3, 2.
Also choose this type. Okay, because the rated power is larger than the PR. Okay, and then we compare the two planes. this type and this type, okay? And then how to choose, how to compare this, we should know the speed ratio, okay? The speed of the roller, we can use this to calculate the speed of the roller, okay? V is the velocity of the belt. D is the diameter of the roller. We have know the V and the D. So the speed of the roller is 65.5 revolution per minute. Okay. And then according to the table, we lose the synchronous speed and load the speed with full load. This is for play 1, which synchronous speed is 1,500. And this is for speed 2, which is synchronous speed is 1,000. And then we use the speed with full load divided by the speed of the ruler, and then to calculate the total speed ratio. All right, calculate the total speed ratio. So for play 1, the total speed ratio is 21.98. For play 2, the total speed ratio is 40.66. So we choose which one? We choose which one? Choose play 1 or play 2? Choose play 1 or play 2? Choose
One.
which one? Oh,
Plane
usually
one,
we
plane one.
choose the little one.
But lucky the plane one is smaller than the roller speed, right?
Play 1
Why
for
did
the
you
fourth
take it?
play 1 is large. The speed ratio is larger than play 2, so we choose play 2.
Yeah. Okay.
Okay.
Okay, because for play 2, it has compact structure, and then it's per meter. The type is this, the rated power is this, and then the synchronous speed is this. And from the table, we can know the uh, uh, we can know the dimension for the motor shaft. Okay, and then we should distribution the speed ratio, and we know that the total speed ratio is this. Okay, and then we choose how to achieve the speed ratio. How to achieve the speed ratio from the motor to the roller. How to achieve the total speed ratio? We use the reducer. Okay, we use reducer. Okay, and we the total in this design, the total speed ratio is the speed ratio of the reducer. Okay, okay, okay. So then we use this to calculate the speed ratio I1, and then calculate the speed ratio I2. Okay, and then we determine the input power and torque and the rotating speed of the shaft. For shaft 0, the motor shaft, the P0 is PR, and N0 is the speed with full load. And then we calculate T0. And for for shaft one, okay. For shaft one, it is shaft, okay. We should consider the efficiency of the coupling, okay, coupling. And for shaft two, we should consider the efficiency of gear and bearing. For shaft three, we should consider the efficiency of gear and bearing. For shaft four, we should consider the efficiency of bearing and coupling. Okay. So, so we calculate for shaft one, it's P0 times the efficiency of coupling, and then N1 is equal to N0, and then we'll calculate the input torque. And then for shaft two, we should consider the efficiency of gear and bearing. And we calculate N2 is N1 divided by the speed ratio, and then calculate the T2. And for shaft three, we should consider the efficiency of gear and bearing, and calculate N3 is N2 divided by the speed ratio. And for shaft four, we should consider the efficiency of coupling and bearing, and N4 is equal to N3, and then calculate P4. And the parameters, many of parameters are listed in the table, okay? And this is for in our course design. There is a word design case, okay? Design case. Okay, this is we have the and our course design is this case one. And this design procedure and the results. The procedure and the results is your design and calculation description, and you should submit the description. You can refer to their calculation and design in this word, but this case was done by a student. The design and calculations are not completely correct. So there are some you should do it by yourself, and you should find the errors in the design, okay? And then you can refer to the design and the calculation procedure, and then you should design a high-speed shaft. So you should join this. You should submit a drawing with the shaft like this, but the dimensions are not correct. The dimensions in this thing are not correct. because there is some errors in the design. Okay. The dimensions are not correct.
Also, we need to draw the shaft by hand.
Uh, you can buy next week